Okay, hello everyone. Let's start the class for today. There are still seats up front, so people please find your seat. Okay, so this class I will first talk about some logistic matters, and then we'll start with our guest speaker. Okay. Okay, so we've seen a number of questions posted on Piazza, and I think students have some questions about the class requirements. So we'll first clarify this. So first of all, class attendance is required for all students. Doesn't matter how many units you are taking it, you are required to attend the class. And then for students who are taking the course for 2 units, which means that you are doing the class project option, then still the class attendance is required, but the reading assignment is only recommended and is not required and will not factor into your grades. Right. So for students who are taking 1 unit or 3 units, as you know, you are taking the reading assignment is required, and you need to do those. But for students who are only taking the course for 2 units, you don't have to do the reading assignment, but it's recommended since it will help you to understand better in class. Okay, so right, for undergrad enrollment, as we mentioned, even though this is a 294 class, we do allow some qualified undergrad students to enroll in class. So for the registration code for the undergrad students, these registration codes have already been issued. So if you are qualified, then in general you should have already received the registration code. And as we mentioned earlier, since this is a graduate level class and meant to be advanced level, so we require students to have basic deep learning experience to enroll in the class. So some of you who really wanted to take the class but haven't received the registration code, in general, that's because you didn't have sufficient deep learning experience to be able to enroll in the class. But however, if you think somehow you can demonstrate that you do have the required basic deep learning experience, you can talk to the TA, Richard, at the end of the class. And if you don't have the background, it's likely that the class will run again in the future. For example, next semester, you can always come back next semester when you do have more experience. And the reason why I'm doing this is actually to ensure that students have a good experience in the class. If you don't have the basic deep learning experience, that means that you will not be able to benefit from the class. And hence, it's to your best interest to take the class in a later semester. Okay, and then for people who are doing the reading assignments, as you know, you are required to submit discussion questions ahead of time. And here, I'll just clarify a couple points. I think some students from the first, the round that we just did for this lecture, when you submitted discussion questions, I think some students had confusion. So let's just clarify this for now. So when you submit the questions, there are 2 types of questions that you need to submit. One's the general technical questions, and one is the paper-specific questions. So even though we separate these into 2 classes, it's still all questions should be technical-oriented questions. So there are questions about certain technical aspects. The reason we separate this into 2 categories is because students may have some technical questions that are related to the general topic of the given lecture, but may not be specific to any of the reading assignments. And we still want to encourage students to think more broadly than just the papers that are assigned for reading. And hence we had this category of questions, discussion questions. And so when you try to think about what questions to submit for discussion questions, for this category, please keep in mind that it's meant to be technical questions. It's not meant to be, what career advice you can give, a type of questions. And these questions should be related to the topic, ideally, of the lecture. But they don't have to be specific to any of the assigned papers. And then the other category is paper-specific questions. As you read the papers, you may have questions about certain technical details, why the experiment is run this way, why the data set is picked this way, what modifications you may make to the architecture, and so on. So those questions related to any specific assigned reading, you list them in the category of paper-specific questions. Okay? And then discussion lead, again, as we mentioned, for students who are taking 1 unit all 3 units, you need to sign up as discussion lead. The sign-up form has already been put up. And if you haven't signed up, you should sign up ASAP. The slots are on the first-come, first-served basis. And you should sign up by this Friday, right, for planning for purposes. And because we have quite a few students in the class, so for each lecture, for the discussion lead, actually it's going to be a group. Usually it'll be 3 or 4 students. And from the sign-up sheet, you can see who else are in the group. And it's your responsibility to coordinate within the group to figure out how you divide the work so that you can do the discussion lead effectively. Right. And then it's important for the discussion lead for that particular lecture that you ensure the timeline is met. Again, the details are on the website and also in the slides from last lecture. As a discussion lead, on Wednesday, you need to send out the questionnaire for people to submit questions. And on Friday, you need to send out the poll. And then I think on Sunday, you need to then send the teaching staff and about the final list of discussion questions. So again, please make sure that the timeline is met. And also for the discussion questionnaire form, you can follow, so Richard has already posted a template. So for future discussion leads, you can follow that template as you send out these forms. And then also the discussion lead at the end in each lecture, you will be leading the discussions. Richard will demonstrate as an example in this lecture, and you can follow his example. Okay, and then for the class projects, for students who are taking 2 units or 3 units, you are required to do a class project. And to help students to get started, we will send out an initial list of suggested class projects to help you, start thinking about what you may want to do. You are not required to pick from this list. This list is only meant as suggestions to help you. And we'll release the initial list by end of day today. And additional suggested class projects may be added later as well. And also for some students, you are already doing a research project, and it's fine to combine your class projects with your research project. And of course, for deep learning, sometimes it requires computation resources. And as the TAs have already posted on Piazza and also listed on the website, there are credits that you can apply as a student. For example, Amazon credits are other cloud platforms. So you are encouraged to start early if you want to apply for those credits, and you can use that for class. And then just in terms of the timeline for the class project, again, the timeline is posted on the website. And here I just want to clarify a few points in terms of the different milestones that we expect. So the proposal is due actually fairly soon, in about, I think, a little bit more than 2 weeks, or just about 2 weeks. So what do we'll send out detailed instructions, what do we expect from each one of these documents and the milestones. So for the proposal, we expect you to already start doing your initial selection of the class project and doing the initial planning. And also, you may need to do some initial literature search, and this will all help scope your project. And then later on, we'll have a milestone number 1. We expect you by that time that you have already completed the literature search that's needed, and you need to finalize your main data set selection if your project often involves data sets, and you need to do initial exploration of the proposed approach already and have initial experimental results. And then you need to provide detailed plan for the approach for next steps. And then by milestone number 2, we expect you to have already done in-depth exploration of the proposed approaches and have detailed experimental results and already gained some insights from these detailed experimental results and make plans for refinements for the next steps. And then finally, we'll have the poster presentation and the final report. And these should contain the summary of your project, in particular your proposed approach, and also demonstrate the results and insights that you learned from the project. Okay, so then the next steps, again, for undergrad students who still need to enroll in the class, you think you need to get registration code, then you need to get it from Richard, the TA. And also, again, we require the students to join the Piazza and also the student Google group. The links are on the website. If you have not joined, or if you did not, for some reason, receive any of the earlier Piazza posts, you should check and you need to join ASAP. And you should start planning for the course project. And you can use the Piazza to look for partners and also check out the list of suggested course projects, which will be released today. And also, if you have not signed up and you are required to, then you need to sign up for the discussion leads. And also for some students, right now on the roster, it shows that you register for blank number of units. So you need to make sure that you are enrolling for the right number of units. And in general, this class, we only allow students to take max 3 units. If for whatever reason you have to take 4 units, you need to come see the instructor after class. And again, if you are right now enrolled for a blank number of units in the system, you should correct it to the right number. Okay, I think that's all I have. Okay, so now Trevor will introduce our guest speaker today.
Great. I'm very pleased to be able to introduce Richard Socker. Richard got his PhD from Stanford University in 2014. And he was one of the early pioneers of the, I would say, the modern era or revisiting of neural approaches to natural language processing, and in particular was one of the avant-garde in terms of looking at vision and language together, although I think he's really focusing mostly on core natural language and related techniques. He founded a company right after his PhD called MetaMind, which was going to take over the world and make AI safe for humanity, which it did, and then was acquired by Salesforce, where he is now chief scientist and probably wants to hire all of you at some point. So
that's right.
Very good.
So first I thought this was a bit more of an advanced lecture, so I was going to go straight into tackling the limits of deep learning for natural language processing. But then over lunch, half an hour ago, I was told, maybe some introductory material would be good. So I'm going to do a survey, and depending on the outcome of the survey, we'll take a short detour around LSTM. So who here is familiar with recurrent neural networks? Good. Who here is familiar with LSTMs and GRUs? Almost every. It's like sort of just around borderline. We'll go over briefly.
Background is always helpful.
Background's always helpful. All right, great. So basically, we're actually at Stanford right now teaching around 700 student class around this material, and this is coming up next week. So I had most of it prepared already. So hopefully you're going to be familiar with most of these equations and concepts, and if not, you can actually go to this website and brush up on it. I think this is sort of the midterm review that we're about to hit. So you should hopefully know word vectors, word2vec, and glove, and how to optimize those and their objective functions. Then you might want to familiarize yourself with simple neural network and max margin training. And then the main backpropagation equations are these two. So if you feel like if this is a simple feed-forward neural network and you can derive to get to these two equations, you will know all of deep learning in most of its form right now, which is like feed-forward neural networks. You just you shoot your error signals down, compute your delta messages, and then you have your final updates for all the different neural network layers in this equation. So I'm assuming since you raised your hand for recurrent neural networks, you know standard feed-forward neural networks and those equations too. So now, usually we will optimize all our recurrent neural networks for language models, for instance, with the standard cross-entropy error. We have some softmax classifier top, and then this is our main recurrent neural network equation. Right, we have some word vector at each time step t, and we have the previous hidden state at the 0th time step. We initialize that some 0 vector or sometimes a small random vector. And then we have here a standard neural network to compute our hidden state. So, and then we compute some kind of softmax at every time step, right? So that's just a standard recurrent neural network definition. We usually have as our objective function the cross-entropy error here, and we usually use mini-batch stochastic gradient descent, where we look at a couple of sentences or short subphrases, depending on your data set, or paragraphs for each mini-batch. All right, so that's kind of what I assume everybody knows. We would spend otherwise, 8 hours talking about all of that to go from 0 to that. Now, we can extend recurrent neural networks in a variety of ways. And I'm sorry, again, I think roughly 2/3 will know all of this, but hopefully it'll be helpful for the other third. So we can make recurrent neural networks much deeper. We can go have multiple layers of recurrent neural networks. And then we often also have bidirectional recurrent neural networks where we go over the same sequence from the left and from the right. And so at each time step, we basically have the context from, in practice, usually around 5 to 10 time steps to the left and to the right of any given word. All right, I'm going to stop there and ask if there are any questions for this sort of basic ramp up, which, yeah, again, we did in 3 minutes, and usually it would be many, many lessons, many lectures. All good? All right, that's either a good sign or a bad sign. Okay, so recurrent neural networks as they are good. Now, it turns out normal recurrent neural networks are very hard to train, largely because of the vanishing gradient problem. And because of that, there are a couple of new types of recurrent units that have been introduced. And I'm actually going in sort of reverse chronological order in the sense that GRUs came much later than LSTMs, but they're simpler. And so pedagogically, it's sort of better to start with. The main idea for GRUs compared to standard recurrent neural networks is that we want to keep around memories to capture these long-distance dependencies, and then we'll want to allow these error messages or error signals, the deltas, to flow at different strengths depending on the input. So the problem here with this kind of equation of a recurrent neural network is we really update the hidden state in its entirety at every time step. Right, so intuitively, even if a word is not supposed to change the content much of that hidden state, it still will. So for instance, let's say you want to do sentiment analysis, and it's a long movie review, and that long movie review talks a lot about the plot, and but in the beginning it said, this movie is pretty bad, but let me still tell you about the plot, and you can make up your own mind. Right? So now really what that means is as you update the plot, that doesn't really matter to the sentiment very much. And so you want to actually keep around that it was bad for as many time steps as you can. And standard recurrent neural networks would use all the content words here that would come through the word vectors xt at each time step and basically update the entire hidden state, eventually completely drowning out the sentiment content of the hidden state. And so GRUs essentially try to fix that. So how do they work? Basically, you have relatively similar standard hidden layer expressions, but you'd actually first compute a couple of so-called gates. And so this is, again, our standard RNN, just to compare. And now instead, the GRU will first compute an update gate, just another layer, that also takes as input the hidden, the current word vector, and the hidden state from the previous time step, and updates this Z gate. And we don't yet know how we'll use it, but we'll get to that in a second. And then we'll also compute a reset gate, which again is just a standard single layer neural network. Now, how are they all put together? It's basically in this equation here, where we compute this new memory content by what looks almost like it, but then you have here this Hadamard product, so just element-wise product. So Z and R T's are also vectors of the same dimensionality as your hidden state. And what you now do is here in this reset gate, you essentially allow the model to decide to potentially ignore the previous hidden state. So if your reset gate is 0, then this whole term goes away, and you just keep around whatever mattered at this time step. So again, with the simple example of sentiment, let's say you talk about the plot the entire time, blah, 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 boy loves girl, didn't work out, blah, blah, blah. And then you say, oh man, and overall this movie was really boring, and the acting was terrible. Now, really, you can wipe out all the previous hidden state, and you only care about the plot being boring and the acting was terrible and so on. And so the reset gate can essentially ignore all the previous context. And now, of course, because this is a vector, it doesn't do it, it's not in its entirety that it will reset that hidden state. It can reset certain units of that hidden state. And usually you have like 100 to maybe 500, most 1,000 hidden units. And some of these can now be closer to 0 and basically get updated based on just the input at that time step. Now, that's basically the intermediate memory content. And now the final step uses the update gate. And the update gate is similar in the intuition to what I just described. But here, we essentially allow the previous hidden state of the memory to be copied over without much modification. So intuitively here, if your update gate is all ones, you can actually just copy over all the content from your previous hidden state. Right? So if z is a vector of all ones, and you multiply these with the previous hidden state, then you basically get that previous hidden state as is, and then 1 minus 1, this goes to 0, and you ignore everything at that time step. And this is, again, intuitively something important happened, something that really matters to your overall objective function, such as in sentiment analysis, some really strong sentiment words, and then comes the plot. You can now keep ignoring the plot, and you can keep around whatever is important to you and your objective function in that hidden state. And then, of course, in reality, it's much more subtle. It's rarely ever fully 0 and 1s, and it's not the whole vector. It's just elements of the vector and so on. All right. Any questions around GRUs? Those are actually like the super important building block for a lot of the models that I'll describe in the second part of the talk. Yeah?
In terms of performance, how does this compare to the traditional track?
It's a good question. So in terms of performance and speed, I assume. So in terms of performance and accuracy, it's usually much, much more accurate. In terms of speed, you can kind of intuitively answer that question by having, you have these three equations here, and they are basically replacing, these four, but really here you have the large matrix multiplications often, and they're replacing this one equation here. So you can intuitively think of this as like maybe 3.5x slower than the traditional RNN. Yeah.
Are you going to talk about LSTMs?
Yes.
Okay.
Yeah.
I'm just wondering, like as somebody who hasn't seen this before,
Mhm.
if I wanted to try to make an update that was just like keep around some of the old hidden state that maybe like reset, the initial thing I would write down would be much simpler than this, right? Like I might say, okay, just do like the standard RNN update and then have like maybe one reset gate. And
Like a single global reset gate?
per time step or
Mhm.
something.
Mhm.
Like why should I do this thing where I'm taking the Hadamard product and then I'm taking the Martin with the weights with the XT and then I'm also recombining it with the update gate? Like that just seems.
So when you think about maybe sort of your first thought is like, oh, I would do something much simpler. When you think about it a little more, this is actually one of the simplest things you could do to have the following two ideas. One, sometimes I want to keep around stuff from the past, and sometimes I want to overwrite stuff from the past. Is there really it's hard to make it even simpler. Here you basically have just the simplest do I want to keep the left or the right with the update gate. But and this can become useful, and it's actually in the second part of the lecture, we will introduce some models that instead of having this full component, they'll actually replace this vector with a single scalar that can that has even more power to keep around the entirety of the vector. But if you want to allow the model to pick up which things matter, and if it's a more complex kind of pattern, then it is actually very intuitive to allow the model to decide, and that's kind of what these allow you to do. It allows the model to decide what to keep around and what to update. Whereas whenever you would design it manually, you have some preconceived notion, and then your model is unlikely to generalize as well. So in terms of a model that can learn when to update and reset, this is kind of the simplest thing. You pipe it through one layer neural net. That neural net decides when to update and when to reset. All right, let's do two more questions. Yeah.
Just to go a little more clarify one point regarding that. So the new memory content already has the reset gate.
That's right.
So it can choose to retain the past memories or not. Why do we need a new choice that seems to be doing the same thing in the final memory?
Good question. So some people feel like there's a little bit of an overlap here, in the sense that if these are all ones, then H tilde will keep around some of it, but it will still update it with the current word vector. So there's still this kind of averaging out here of the word content. And if you want to be even stronger and not let a certain unit at all be modified by a certain word as it comes in, then you still need that second update gate. Yeah.
So to be able to retain or override information, the network has to somehow know which information is interesting. What kind of features do networks generally use to know which features are interesting?
It's a good question. So how does the model actually decide this? And the beauty is, so I guess intuitively we never decide on this prior to the task. It's all about your objective function and then your model figured out. And I can pull up one visualization of not exactly this model, but of another one that will give you some intuition. It's not always easy to interpret exactly which single unit does something, because these are distributed representation. They often get their meaning through the interplay of many different kinds of features, and eventually it becomes hard for people to interpret what's actually going on in that interplay of 1,000 different units, right? It's like, oh, there might be some very concrete things, like if these 50 units have values in those 50 different ranges, then this thing is more likely to come out as a class, but it's often hard for us to have a very simple interpretation of what's going on, which honestly is like intuitive in the sense that for any complex decision process that people have, yes, we can sometimes come up with post hoc descriptions of why we made that decision, but a lot of times it's also hard, and especially as it gets to fuzzier things like computer vision, it's hard to say, oh yeah, I think this is a person because of these 5 neurons in my brain. It's kind of like that. But in general, there's some interesting work and actually more, I think, coming up in the future around creating more interpretable results, but it kind of goes too far off. All right, one last question. Do the biases matter? Sometimes people add biases here. Sometimes they don't. There's actually sometimes it matters, and in most cases it doesn't. I kind of assume that we add here a 1 to the hidden state and potentially here 2, and then you basically just have an additional column here at the end, and you multiply it with an added 1. Yeah, so I just kind of drop it for simplicity, but you can assume in many cases that you have a bias term here. And it actually can matter how you initialize that. You want to ideally initialize your model such that it doesn't have a strong opinion on having to update all the time or not having to update all the time. So usually you initialize your biases to 0. All right, now there are a couple of attempts on visualizing a GRU. I honestly, personally feel like these equations are so intuitive that I don't know if those kind of visualizations help that much, but you have here your previous inputs. You have your previous reset gates. They don't update the next hidden state gates. The memory doesn't either. The only thing that will update the next hidden state is ht-1, final one. And then your xt kind of goes as input to the reset gate, the update gate, and sort of short circuit connections. And then this is sort of an attempt to visualize the gating mechanisms. So often we call these Hadamard products. The final gates are the gates, and then they modify the hidden state through these Hadamard products. All right, so I think we covered all the intuition about these already. Main thing here is because of this, you now have less of a vanishing gradient problem, right? So if you have your error signal at time step 100 and you want to backpropagate, you, in general, because of standard recurrent neural networks having derivatives here of the sigmoid, which usually are smaller than 1, as you multiply a number smaller than 1 too many times, they go to 0. But here, if your update gate is 1, you really can basically bring your error and your gradient through these hidden states in a much more less diminishing kind of way. So if the update gate here is 1, then really your gradient flows through directly to the previous hidden state, all the way to where the model actually thinks it mattered at that certain time step. There's another attempt at an illustration of the GRU. I don't know. Sometimes it works well for different people, but I don't find them that great. And then usually I start and ask people to derive like all the gory updates and derivatives for backpropagation. And so really the only novelty for them at this point here is as a derivative of these element-wise products. But in general, I think it's good to derive backprop once for the equations I gave in the beginning of the talk, but after that you can kind of assume it can be automatically differentiated. All right, now those were GRUs, and we already had the question on LSTMs from the gentleman here in the front. Now the LSTMs are essentially trying to capture similar ideas, but it's even more complex and they have a little bit more representational power. So now you have a very explicit input gate, which again, if the input gate is very large, the input matters a lot more to that hidden state. And that's independent of a forget gate. You can also make independent of the input forgetting decisions. Again, these are all vectors and can act differently on different on the hidden state and on different units of that state. And then you also have an output gate, which essentially can say, well, this is all important and it should be forgotten in this ratio and updated in that ratio, but it might not be surfaced to the final classifier just yet. So that is an additional output gate. And so here you have your new memory cell. So all of these are essentially the same kinds of just single layer neural network things, but this one is usually 10H. Can actually also be a rectified linear unit, but I think 10H still works best in most cases. And now we'll basically have our final memory cell, which again is not the final hidden state, but the final memory cell combines the forget gate with the previous memory cell and the input gate with that new memory cell coming from here. And then you can decide which ones of these you want to surface to your hidden state. So the final hidden state can be not as modified, but you can still keep around memories for many time steps. So there's this additional separation. Yeah? Why 10H? So intuitively here, because of these gates, you want to keep around these two to be in roughly the same value. In general, I think why 10H is kind of a historical decision too. It's sort of the most, it's often a unit that behaves slightly better in optimization than a pure sigmoid, where the values are between 0 and 1, and you want to have some negative values also. And then it's kind of the traditionally default nonlinearity that you used. Now, on top of that here, it's especially good to have these different values be in a similar kind of range to be not, you don't want one to be much larger than the other. And so this kind of normalizes the range too. All right, so that's the LSTM. And that's, sort of blast from the past. It's been introduced many decades ago, but it's made a big comeback, and it's a very powerful model, and it's often now in models you just see LSTM block. You can also stack these up so that you replace in the next hidden layer, instead of having xt here as input everywhere, you'll have the previous layer's ht at that time step. And so you can stack the LSTMs also really deeply.
So
Yeah.
why did
Sorry, what?
they come out with GRUs more recently if LSTMs are so effective?
Jürgen Schmidhuber will have a different answer to that. To him, a GRU is really just an ablation of an LSTM. And he feels like it's a very superfluous paper that wasn't really necessary.
Why did you bring it up?
Pedagogical reasons, like I mentioned in the beginning. I think the GRU is more intuitive. In some cases, so personally in our group, we often have a hyperparameter that says, should we use an LSTM or GRU unit? And if the GRU works just as well, it's always preferable because it has fewer updates, fewer parameters, it's faster to compute. So it's kind of a simplified LSTM cell that is faster and in many cases works just as well. So yeah, sometimes papers just say, oh, look, this previous complex model wasn't as necessary as we thought. And again, there are a bunch of attempts at visualizing the LSTM. Again, I feel like in many cases, I don't know if this is really helping anybody understand it. But you can kind of get the idea here. You have your memory inputs, you have your forget gates that keep going around. But then in theory, all of these are kind of simplifying it because you kind of goes around in circles here too, just like the forget gate. But yeah, different people attempt to describe them in different ways. All right. So now we're all on the same page with GRUs and LSTMs, and we can jump to the fun stuff, which is tackling the limits of deep learning for natural language processing. And this is joint work with a couple of folks on our research team, sort of sometimes called the Einstein research team. Einstein's just sort of our mascot for all the AI stuff at Salesforce, and then also 2 students who I was mentoring for a class project last year at the Deep Learning for NLP class. All right, so basically, I think the limit that we're about to hit, or that we're hitting now, is that the field of AI has gotten really, really good at taking a single data set, task, model, and metric, and then optimizing in this setting with, again, a single data set, task, model, and metric. And thanks to these end-to-end deep trainable models, the speed of the improvements on these single tasks is increasing more and more. However, if we continue to start all our projects from random parameters, we won't ever obtain a single NLP model that can understand language in all of its complexity. Right? It's just like, it's as if you teach a kid something, and every time it learned a new skill, you whack it over the head, make it forget that old skill, and start teaching it a new skill. And so I also think a single unsupervised task is unlikely to solve this problem, since language has a lot of different kinds of supervision, social, emotional, and whatnot, and lots of different kinds of feedback. And I think in the end, requires us to solve a whole host of different kinds of tasks, right? You can read a book or a paragraph with something in mind, and that will make you read that paragraph very differently. You can have a social interaction. You're trying to convince somebody of something, and that will trigger a lot of other kinds of cognitive skills that will then all drive how you use language. So that led me up to the question of how we can express these different tasks in the same framework. And we do have inside NLP different kinds of ways we think. Some people think a lot about sequence tagging tasks, like name entity recognition, part of speech tagging, and so on. Sentence level classification, a lot of times that's how sentiment is cast. Or sequence-to-sequence models where we have input in one language and we want to translate it to another language in machine translation, for example. And so I think the framework for tackling NLP that is a little more comprehensive and all-encompassing, and that we're sort of working towards in a lot of different kinds of ways, is to have a joint model, a single joint model for comprehensive question answering. And what do I mean by comprehensive question answering? Here are a couple of such tasks. The first one is kind of the standard task that people would associate with question answering, where we have a couple of simple facts. Mary walked to the bathrooms, and I went to the garden, and so on, and we ask, where's the milk? And now you have to kind of reason a little bit about this, and this is not very hard, right? If you had exactly these kinds of expressions, only you could probably write a regular expression to solve that exact thing. But ideally, you'd have a model that can pick up whatever you as a human would write in that regular expression. Now, another task could be another sort of input question-answer triplet, could be everybody's happy, and the question is what's the sentiment, and the answer is it's positive. Now, in many cases, sort of historically and sociologically in the research community, those are 2 very different sets of people. Some work on logical reasoning, and others work on sentiment analysis, and they use very different kinds of models in many cases, though I guess thanks to deep learning, more and more de facto default is they use some kind of deep recurrent neural network, but it's still very different thought patterns in most cases. And then it's even more true for the machine translation community, which unlike the logical reasoning community always has to deal with gigantic data sets, and hence will only work with models that can scale really well. But in some sense, it's also another way of casting it as a question answering problem. Like it's another type of question answering problem. So you have some input, the question is in what language to translate it into, and the answer is that language. And then if you think about everything just in terms of sequences, you can also cast images into that framework by saying, well, images are sequences of pixels or sequences of regions of pixels. And those can be inputs as well, and you can ask questions about those also. And so really the idea here, if we want to have all of these as input, is we have to take the question as another input in our training data sets. So instead of having the standard sort of xi, yi kind of framework, we have xi, qi, yi. And when we have the question as input to the model as well, then we have some kind of hope that we can have a single model where actually everything is shared. Now, once you have that goal, there's a lot of issues that come up. It's really non-trivial, and it'll take many years to actually get there. Again, part of that is that we're so ingrained in this performance on this task. So if, even just trying to publish a paper with 5 tasks, you kind of have to do well on all 5 of them, as well as people who have tuned their architectures to only a single one. And so the first major obstacle of the 6 that I'll describe in this talk, depending on how far we get, is that there's not even a single model, not even a single architecture that could tackle and get state-of-the-art results on all these different kinds of problems. So for question, and this is of course before we published the first paper that I'll talk about, but in end of 2015, there are 3 different kinds of models for question answering, sentiment analysis, and part-of-speech tagging. You do notice that there's some kind of neural network in all of them now, but one uses tree structures, the other one is bidirectional LSTM with some conditional random field on top, and then this one is quite a tuned architecture for this particular data set, strongly supervised memory networks. And so to tackle this first obstacle, we introduced at ICML last year the dynamic memory network. So let's walk through this. Fortunately, now that we know GRUs, you know most of the important parts of this model. Namely, whenever you see sort of lines like this, these are the hidden states of a GRU, and the line through it is basically we're connecting them. So each of these is a type of GRU. And so we always start with a question. So for instance, where is the football is the question here. And then we have some kind of input, and we run a GRU over this, and we take the last hidden state of the GRU, and we call that the question vector. Then we have, independent of the question, we have an input module, which is also just a GRU that runs over the inputs and computes at every word and at every sentence a hidden state. And then we basically want to reinterpret this input conditioned on this question. So when you say, where's the football, you do have a abstract representation for the input, but now you also want to say, well, not all of these seem relevant for this question. So let me trigger an attention mechanism that, given this question, will reinterpret this input and pick out only the kinds of sentences and words that really matter. So in this case here, whereas the football goes over the input, and we'll define how we exactly compute this attention gate, but basically it will pay attention to some of these, and in the first iteration, we'll say, all right, it seems like the last time the football was mentioned is the most important thing because the question is about the football. And so this will get a very large gate, very large sort of input, namely in this case 1.0. This is actually a synthetic data set, which in some ways is a regression for the NLP community, but it's an interesting kind of necessary but not sufficient condition kind of data set where if you can't even solve that problem, you probably can't solve more complex NLP and question answering problems. But being able to solve that problem doesn't mean you actually solved question answering in its all its glory. All right, so now basically what this model does is, with this question in mind, it will trigger an attention mechanism. When it finds something that seems relevant at the time, namely things that mention football, then it will give that as input to another GRU type model, and it will agglomerate all the facts from the input. And at the end, it will kind of have some sense of how this input relates to this question. But the problem here is that whereas the football really paid attention to only John put down the football, so now it knows in this vector there's something stored around football and John. John now seems also relevant to answering this question. And so it will now go over the input again a second time, but now not just taking the question into consideration, but also the previous memory state. And with that memory state and the question in mind, it will go over the input again, now looking for not just football, but also John. And it finds the last point where John was mentioned and gives that a very large attention, agglomerates that in our hidden state of the GRU, and then gives that final hidden state as input to the answer module, which is yet another GRU that generates sequences just like a standard recurrent neural network that we might use for machine translation or any other kind of output task. All right, so that's sort of the full model in its glory. Now they're mostly just GRUs, and so the basic building block here is really just type of recurrent neural network, there are two interesting subtleties, and that is that instead of having a plain GRU, we actually make it even more extreme. We have a single gate. So this GIT here is for the tth iteration over the entire input, and the ith time step, the ith sentence, for instance, this can basically, with a single scalar, decide whether we want to use this input or not. And then we use the entirety of the vector. So this can be kind of seen as a global gate on top of a GRU. And basically, if that's the case, we can just entirely copy over previous hidden states. And that's basically because questions like this, and where's the football, it really is completely irrelevant that Mary traveled to the hallway, right? And we just want to be able to drown that fact out entirely and just keep around states or facts about John and the football. Now, how do we compute these gates? This looks kind of complicated, but it's also actually quite intuitive. Basically, we just compute a couple of different multiplicative and additive kinds of element-wise similarities between a sentence vector, the question vector, and the sentence vector and the memory vector, and then again, sentence and question and sentence and memory, but absolute values of the differences of each of the units. So all of these are element-wise. That becomes one large vector that basically captures similarities between all these different vectors. Intuitively, if the question has something remaining of John in it, and the sentence has something, that the vector John modified, then that we'll have some large elements, and then we pipe that through a two-layer neural network, put a softmax on top, and that's it. All right. Any questions around the dynamic memory network? Yeah. It's a great question. Why didn't we choose not bilinear pooling? We actually used to have bilinear pooling in here, and that was the first iteration we submitted to the conference to. But then we ran some more ablations with some more GPU time, and we realized it just doesn't add much, or it doesn't add anything in terms of performance. So we took it out. We do have the Hadamard product in here.
But did you try removing that?
Oh yeah. So this is like the smallest set that didn't hurt performance. Yeah, and that's often. A lot of the times when you're sort of pushing the boundaries of new kinds of architectures, you gain some intuitions. And my intuition was, some kind of bilinear product, or maybe even, S transpose times some matrix times the memory state and so on would help. But the best thing to do if you have some extra GPU time or CPU cycles or whatever is to just try it out and run some cross-validation over your development set and then make sure your intuitions are really true. And so in this case, we're able to simplify it a little bit more. All right, so there's at the time, there are a lot of other kinds of sequence-to-sequence and memory architectures. And I think the closest one, sort of the memory networks, are actually developed in parallel to our work, but came out in archive a little bit before ours. And so I think the main difference to memory networks from Jason Weston here is that the main similarity is that they also have some kinds of input, scoring, attention, and response mechanisms. But for them, each of these mechanisms is a different type of architecture, a different kind of model. And we try to have a single basic sort of Lego or building block behind all of them, namely some kind of recurrent neural network like a GRU. And with that, because it's a sequence model, we can also more naturally capture the position and the temporal kind of sequence patterns. And that kind of allowed us to not just work on the Babby data set, which is these simple kinds of questions like John put down the football and things like that, but also do sentiment analysis and sequence tagging and so on. And so you might ask, how important is it to actually have these multiple iterations here over your input? And in some cases, it actually matters a lot. So if you have three different facts, so some kind of transitive reasoning, like if A to B and B to C and C to D, then you can make the final A to D kind of conclusion. You really have to have multiple passes. It's just impossible for the data for any model to figure that out, right? It's like if you only pass over the data set once, and you ask where's the football, and the last sentence is John put down the football, you just can't answer where it is because you need to go over another pass over it and figure out where John actually is. And so intuitively, it makes a lot of sense. Now, the reason why we aren't able to tackle the full problem here, which is a joined model versus just the same kind of architecture, is that this hyperparameter of how many passes do we have to do over the data set is actually different if we apply it to sentiment analysis. So for sentiment analysis, 2 passes actually is the best, and if you do more, it actually gets worse. So this is why there's still, of course, always more research needed. Yeah?
How good is the Babby data set? Is it like the ImageNet for vision?
Oh, not at all. No, it's not great.
Because you're just not ready for something more realistic?
We will get to something a lot more realistic very soon. But to me, it's kind of a necessary but not sufficient kind of data set. It's like if you can't even do that, you won't be able to do more complex things. But being able to do that does not mean you can do more complex things. So it's an interesting question, and I am actively researching right now the ImageNet CNN of NLP and what that could be. And well, I don't want to take away the thunder of my group, but yeah, it's a good question, and I think we're finally making some progress on it. It cannot be a single task, let's just put it that way, because language is more complex.
Question and answer data sets?
Yes, but we'll get to that actually very soon. All right, so let's analyze a little bit what happens for sentiment, which is a little more real. So the Babby data set is actually a synthetic data set, which again is like kind of a regression for NLP, which had stopped using synthetic data sets many decades ago and works with real language data. And so it's fun to see what the model actually does. So here we chose a couple of examples of sentences that were incorrect. So this is the most accurate model for the Stanford Sentiment Tree Bank right now. So it's movie review sentiment. Movie reviews are kind of interesting because a lot of times reviewers of movies try to be very clever and have very interesting kinds of patterns and phrases that they use and kind of witty language. And so here are some examples where even the DMN with a single iteration, a single pass over the input, does not get the right answer. But then once you have 2 iterations over the inputs, you get the right answer. And so the sentences, in its ragged, cheap, and unassuming way, the movie works. And so when you only allow a model that's just trained with a single pass only ever, it's kind of like it puts attention to ragged, cheap, and unassuming, and movie, and works, and so on. And it's like it's not quite sure what to do. If you allow it to have 2 passes during training, and this is, of course, like a dev test example, it's sort of like, OK, well, maybe cheap and unassuming and works are sort of all kind of important, but on the second pass, it kind of agglomerated the facts that seemed relevant for this overall sentence, and then it focuses on unassuming and working and answers correctly that this is positive. Another one here, the film starts out as competent but unremarkable and gradually grows into something of considerable power. So here again, pays attention in the beginning, competent, and everything else a little bit, but then at the end really focuses on a little bit on unremarkable still also, but then grows in power, and eventually the power is the most positive thing. And kind of intuitively, we would like to think it got the gist of the sentence, and then by reinterpreting it again, has the power to focus these attention gates, G, on different parts. And here's the last one, which is my response to the film is best described as lukewarm. If you ever work on sentiment and use a simple kind of model, unigram, bigram type model, then best is usually the one that comes out on top as having the largest weight for being in the positive class or for indicating a positive class. And so the model also can't help on the first pass over the data set to put a very high attention on the word best. But on the second pass, it actually lowers it considerably and then adds the one to lukewarm, reinterprets the input, and actually realizes this is overall negative. All right, now last year we had Tsai-Ming join us as a postdoc from UCLA before, and he is more of a vision guy. And I told him, I was all excited, he's joining the group, and I'm like, oh, the DMN, maybe we can use it for all the things. And he, with his vision background, basically said, all right, well, let's change the input module. I actually also, part of what I'm trying to push for this DMN is to think about these larger neural network architectures in a little bit of a more modularized kind of way, where you can try to replace one module but keep the other stuff intact. And here, in this case, he didn't touch literally the code of the other modules, the episodic memory, answer, and question module, and he only changed the input module to essentially give us some kind of sequence over patches of an image. And so the way we did that is basically we ran a standard CNN, and then the last layer has sort of 14 by 14 blocks, and each block has associated with it a feature vector, and then those were given as input to a bidirectional GRU. And that's why I went over to GRU in the beginning, so we all know what we mean by this kind of block now. And so this is basically now the input, and here on top of these you can compute all your attention gates and everything, the question comes in and all that. And somewhat to our surprise, this almost never happens, but on the second experiment we actually got the state-of-the-art result on the VQA dataset with keeping everything intact. This was also his first Torch project. I worked in MATLAB and other languages before, and so like it was really not touched. And this is also, this is a great data set and I think a great sort of new research pattern that's emerging with us.
Debbie spoke last week.
Oh, awesome. All right, you're all set on that. So I love Debbie's work. We have another paper in submission right now together on image captioning. And so I love, and you have to give Microsoft a lot of credit too here. Basically, they have a whole server infrastructure up and running, and I'm guessing she talked about that too, the server infrastructure. No? Okay, well, so basically, it's a really sort of private test set. You don't get to cheat by training a little bit on your test set and so on. You just have to submit your answers, and then you get the scores back, which is great. And there's only one more level. I think you actually compute the outputs on the test set yourself, but you don't know the official answers. But if you really wanted to, you could probably still cheat. The SQUAD data set, the Stanford question answering data set, goes one level higher where you have to submit your code, and you never get to even see the test set. But I love this idea of having servers to not destroy our standard and common benchmark data sets. So what's happening to the attention here? So remember these gates G, these guys here? So this is basically a visualization in the image world of what happens when they're large. So when this area here is brighter, the G attention that is given to that one of these 14 by 14 blocks is brighter. And so the question is the question, the input, and the answer that this model gives on these development test set images. So the answer here is metal, and it pays attention to this big center structure. I was like, okay, actually, let me start with these. So what is the main color on the bus? Again, pays attention to the bus and says blue. If average, like sort of majority color here could be more green. But it's still kind of the main center object, so it's not super impressive, and it's paying a lot of attention to it. What types of trees are in the background? Answer pine. This one's kind of interesting. How many pink flags are there? And pays attention to those 2 pink flags for the most part and says 2. Now, the truth is that we're actually not that great in general on number questions. Nobody really is. We only get a little bit more than a third of those correct. And we also only get number questions right with small numbers. Like you can't give it like a picture like of this crowd and say how many people are in here, and like actually give like 80 something. Largely because the final thing here is also softmax classifier still, and if the softmax classifier hasn't seen a certain class, it's never going to predict that as an answer. There are, however, still some interesting things that eventually made me think this is more than just sort of random, and the attention is actually really capturing interesting patterns. So is this in the wild? Kind of pays attention to the structure. And then you are also worried, and we're not the only ones, that maybe only with the question you can actually do quite well. And it's true that if you just look at the question, you can get around 48% of them correctly. And so this is one of the few where that would trip you up. Because if you ask the question, what color are the bananas, and you ignore the image, you would just say yellow. But in this particular image, it actually does pay attention to the bananas, and then they're not yet ripe, so they're actually green. So it kind of overrules a language prior that we might have. What is the pattern on the cat's fur on its tail? Pays most of its attention to the little tail here and says stripes. And in general, that's actually like surprisingly accurate. And of course, I think sometimes you can't overinterpret it too much. So who is on both photos? It just kind of basically finds the majority kind of most likely person object type in the picture. and says girl. It doesn't really have an idea of realizing there are two pictures and then mapping and making sure they're the same and so on in terms of the both photos. It's just like who's in the photo probably would have given a similar kind of activation here. But again, if it learned about a certain pattern, it actually gets quite good. So we then created a live demo, and we'll actually, if the internet works, we can play around with it a little bit. But here's an example that I showed a reporter from the New York Times, and we just had hacked up the demo the night before, and it's all kind of slow still, and I showed him one question. He's like, okay, I want to type in my own question. And I'm like, okay, he's going to take sample size of 1, and if it works, the article will come out great, and if it doesn't, he's like, maybe not. And so he wrote, like, is the girl wearing a hat? And like, it wasn't like a production level system. It was just a quick hacky prototype. So it was like churning for a while, sending the pictures back and forth in very inefficient ways. And so I was already coming up with like excuses of like, well, the hat's kind of hard to see. It's black and black background. Like, can't really blame the model if it does. And then it said yes. I'm like, all right. Totally saw that coming. And so after the interview, I then like played around with it myself. And these were literally the first, like the next 7 kinds of questions that I asked it. And basically it has seen, of course there's no magic here, right? It has to have seen other tennis images. But like there's still some kinds of questions that would be different for different tennis images. And so what is the girl wearing? Shorts, and what is the color on of the ground? Brown. And then it's like, okay, well, what is the color of the ball? Right? It's like one of the smallest objects in the image, and it still gets it right. And you can also it's interesting, you ask was she wearing shorts, but then if you ask what's the color of her skirt, it still says white, so it's kind of, it's actually a little ambiguous what it is. And then this one, like, what did the girl just hit? Tennis ball? And then I was like, oh, now maybe I can think of a way to break it. And I asked, did the girl just hit the ball? And it said yes. And then I asked, is the girl about to hit the ball? And it also said yes. And then I was like, all right, that was the first one that I could break it. So we can kind of go over a little bit of a demo of this model. So this is the dynamic memory network, and I can't really see it here. All right. So this is a fun sentence that was in the dev test data set of the Stanford Sentiment Tree Bank. The best way to hope for any chance of enjoying this film is by lowering your expectations. Again, this is the kind of sentence that most traditional models would get totally wrong because it has, best and hope and enjoying and so on. But this model actually realizes it's negative. And there are a lot of other fun things that sort of traditional models would trip over, like this movie doesn't care about cleverness, wit, or any other kind of intelligent humor. And you ask sentiment, and does realize it's actually very negative despite having cleverness, wit, and other kinds of intelligent humor. But you could also say, it's not like it totally just remembers all of these things. So this movie cares about cleverness, wit, and other kinds of intelligent humor. So very small modification, but now actually, does realize, yeah, those things are generally positive. It's just that there wasn't a negation. Yeah. How are we doing tokenization? Basically, for this data set, it was actually pre-processed to be split with the Stanford Core NLP package. And so it does split on the dozen, for instance. I just kept that. And then a couple of other things that didn't make it into the paper. It's actually, sometimes I feel like papers are like castles. And the bigger they are and the more beautiful they are, the easier they're to be attacked. And this paper, in the first submission, we had 5 different data sets and 5 state-of-the-art results. And then 2 of them, we didn't have any nice ablations, any good analysis. And then the reviewers just jumped on those 2 and rejected the paper. And I'm like, this was my best SNP submission and my first SNPs rejection. It was like so frustrating. So anyway, so a couple of things that didn't make it into the paper is like, it works for any language. It's just a sequence of tokens. So it's also really accurate for Chinese. You can also ask it, like, what are named entities? And so you trigger the answer module, not just at the end of the input, but at every single time step. It gives you a very accurate named entity recognition system that basically identifies locations, organizations, and people. It's just a sequence tagging problem. And then here, these visual question answering problems. That image is very large. What are men wearing on the head? This is a data set. And I don't know, I think you can ask like a lot of different kinds of questions, like what is in the background, or something like that. And no, trees. And so on. Like, there are a couple of other things, like why are the men wearing helmets? And the answer is safety. So, safety third. All right. So yeah, so this, we can maybe, if we have some time, how much more time do we have until when? 15 minutes? 1-5? Okay, so maybe we did like a little bit fast. Oh, with the questions, 15? Oh, including questions? Oh boy. Well, we'll probably skip most of the other obstacles, but this one is very close to my heart, so maybe we'll spend majority of time on that. Basically, this is the second obstacle, which is, the first one, yes, we have the single architecture that can do some pretty high-level tasks, but to have a single model where all the weights are actually shared is really still hard. And whenever people do that, and by single model, I mean really like everything is the same, including the output, like the classifiers or the decoders in the sequence-to-sequence models. It's incredibly hard. And when people do that, they usually restrict it to just the lower layers. Like word vectors now, everybody kind of pre-initializes for different things. But in many cases, multitask learning for people means you have two tasks. That's the multi. And you have a source and a target task. And you just evaluate on the target task in the end, and you ignore your source task. So for instance, everybody takes a ImageNet pre-trained CNN and then runs it on some other task. But they don't go back and say, oh, how much did it actually hurt CNN ImageNet performance when we updated with this new task? And so, the vision community is further ahead in that sense than the NLP community, in that they are using more of the hidden layers of a CNN for subsequent tasks, whereas in NLP, where everybody just uses word vectors, and when you just try a very simple vanilla kind of, oh, let's just take the same LSTM we train on part of speech tagging or machine translation or something, and put another task on top, it actually doesn't work very well. So there's more complexity there. And so this is a paper from one of our interns. If you want to do an internship this summer, ping me. Kazuma from Japan, and he created this kind of beautiful / monstrous kind of model, where basically on a high level we take some very simple things like word representations are based on characters and word vectors, so a mix of both. It's always like concatenated together. And then you have a couple of tasks that are word level, sentence level, and then multi-sentence level. Kind of intuitive linguistically. And so whenever you solve a certain task, you actually give not just the hidden state of that, but also the output of the classifier of each of them as input to all the subsequent tasks. So you have a lot of short circuit connections to different tasks. And so this model got almost state-of-the-art in part of speech, but this is like a super done task, and it's not very interesting anymore. It's been around for over 20 years, and it's just like, tiny differences like 0.001 or something. Chunking got the state-of-the-art, so trying to find sort of noun phrases that make sense together. Dependency parsing is a very novel, much simpler model. Most, who here is familiar with parsing in general? Not very many people. Okay, so generally you try to find like the syntactic structure of a sentence. Like, oh, this verb has this kind of modifier. It's like running fast. Fast is modifying, and we're running fast together, and together is like modifying we, and all those kinds of things. And usually you run very complex beam search or A-star search kinds of algorithms to find these global structures of grammar in the sentence. And oh no, sorry. Cannot share that. So usually you can't really share, you have to run these search algorithms on top of the decisions for parsing, but here we just have a feed-forward computation. We just have all the pairs of hidden states for different words, and we basically make classifications. And the amazing thing is, in over 98% or so of all the cases, it still comes out with a globally consistent tree structure. And if only 80 or so cases in total, it has like multiple roots of a tree or something like that. Anyway, so the main building blocks here are LSTMs. So you basically just have a bunch of LSTMs, and they all feed into each other, and then you have the overall thing. What was important is how we trained it. And the main idea here is you actually regularize the lower layers of the model to not change too much. So what does that mean? We start with POS training, but then on top of that, we train entailment and chunking and dependency parsing and so on. And as we do that, we still allow the higher level tasks to modify and update the weights of the lower level LSTMs, but we don't want them to change those weights and those parameters sort of summarized here as theta too much. Too much being, depending on this term delta here. And so yeah, it's quite amazing sort of 4 state-of-the-art results when we train all of these different tasks jointly. All right, and so just as summarizing the last couple of obstacles here, one problem with all of these models that I described is we use only this cross-entropy loss, and we have a standard softmax. But sometimes you want to predict words that you've never seen before at training time. And so this idea basically tries to solve that, which is you combine a pointer that can point to previous words in the context with the standard softmax. So if I introduce a new word like Yellen, which I may have never seen before at training time, but now from this kind of sentence, Fed Chair Janet Yellen, blah, 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 raised some taxes, and then misses. Now, most people from having read this would know, oh, it's probably Yellen has very high probability of being mentioned again. And this model can now learn to either point to previous words or use the standard softmax classifier, and has basically a mixture model between these two. And that improved the perplexity, sort of how good are you at predicting next words and the probabilities of next word, significantly reduced that with a relatively small model overall. But then, and this kind of shows you how fast the field is moving now, some of my students had the idea of, well, really, when in all these deep learning models for NLP, we actually also have 2 word representations, an input and output representation. We have the word vectors, and we have the softmax weights. And if the output of the softmax is yet again a set of words, then that means each row of your softmax is essentially also a word vector representation. And so what they did is they actually tied the softmax weights and the word vectors together. And usually in deep learning for NLP models, those are the largest sets of parameters, right? You have a vocabulary of 100,000 words. Each word has 100 dimensions, so you have a lot of parameters. Here, when you tie them, you save a lot of parameters, and you actually lowered the perplexity even more when we tie them. And so I don't think we have enough time now to go through this model in too many details here, but basically, what we observed with the dynamic memory network is that the question was really had this independent vector Q, right? And we didn't really reinterpret the question based on the input. But sometimes the context can really modify how you should interpret the question as well, not just the other way around. So for instance, if I say, may I cut you? That's a very different interpretation if I'm holding a knife or whether you stand in line, right? So you reinterpret that question very, very differently. And so this model basically introduced this interesting co-attention network or encoder where you have a bunch of cross products between the question and the documents.
Can we save 5 minutes for questions?
Right now?
No.
All right. Stanford question answering data set. Check it out. Go to Squad Explorer. It's one of the coolest question answering data sets. Has a great, Percy Liang's doing a great job at kind of allowing you to upload your code. Nobody ever sees the test set. And there are a lot of people who are working on it, and it's quite a great data set. And then we'll skip the QRNNs, but those were visualized, yeah. Anyway, all right, so with that, I hope I could show you and convince you that it's an exciting new goal to try to think of a single model to capture multiple different problems and domains instead of keeping sort of siloed problem-solving techniques. And once you embark on that journey, there are a lot of different obstacles you can tackle that I think can push the field of deep learning and NLP forward. And I'll end with a shameless plug. If this is interesting to you, we're looking for interns and full-time researchers. All right, thank you.
Thank you for sacrificing some of your material for that excellent background. I thought it was very, very good. And we have some questions Richard will.
Yeah, actually, so I emailed you the questions. Could you put that up on the screen?
I know Marty had a question she was trying to get in.
No, I'll look up the paper. It's all right.
Okay, or maybe in the interest of time, I can just read the question
Sure.
that I have here. So what's your opinion on applying NLP models such as attention network to time series-like financial data?
So I think that's a great idea. I actually think part of the reason I'm so excited about having a recurrent neural network as sort of the basic building block is that you can really use these models for any kind of temporal sequence model. We're able to transfer the dynamic memory network quite easily to images just by having a CNN as a pre-processing step and then having a sequence of feature vectors for the regions of an image. And so yeah, I think it also makes sense on financial time data. You just need to have the right kind of data set of question-answer input triplets.
Okay, so since we have 2 minutes left, let's see if we can cover 2 more questions. So if you scroll down to that section, yes. Why were the documents and questions embedded with nearly the same representation? Shouldn't there be a fundamental difference between the two?
Between documents and questions, so you can actually tie the weights of those two GRUs. It's a small hyperparameter. So I don't think there should be a fundamental difference in the sense that in the end you have a lot of symmetric similarity functions. The Hadamard products, the distances and so on of absolute values. And so I think you want to capture that, if you ask a question about John and football, that it has the same representation of football in the question and the input document. So there's actually some arguments for why it makes sense for them to live in the same space.
All right, so let's return to the general questions which are at the top of the document. Sorry. So the second question from the section is long, but at the end it asks, are there steps that you think we should be making as a community to work towards systems which demonstrate more natural language understanding?
Yeah, and I guess the person asking the question didn't see my talk, but yeah, I think that is, there's the 2 papers were in there, but yeah, I totally think we should really think about comprehensive question answering as a framework that can tackle all these different things. Now is the question, what exactly is the model that can answer lots of different kinds of questions?
All right, so I think that's a good segue into the next question. So we see the progress of increasingly complex architectures to accomplish better results. Are there deep learning approaches which focus on building models with less complex parts? Do you think that the old feature engineering techniques are going to make a comeback? So that's the third question.
So I don't think the old feature engineering things will come back. They may come back in some ways through a backdoor of data set engineering. So instead of architecture engineering, you kind of say, well, there's certain patterns and I know they will come up, but I don't want to now modify my whole model because it's a very general model. All I need to do is I add some more training data. And so we'll see, the Bobby data set was completely artificial synthetic data set. Squad isn't, but you could also think about asking more questions and generate more questions on top of Squad. So maybe there might come up like data set engineering as a mix of naturally occurring data with some other patterns that we would like to see being picked up and hence have to teach the algorithm properly with. And maybe there some of these older linguistic techniques could come in. And similar sort of data set enhancement, like in computer vision, when you want to train the state-of-the-art ImageNet kind of model, you rotate your images, you crop them in different ways, you change the hue, you change, you make some grayscale and change color schemes, all these things. And so it's less obvious what those kinds of modifications are for NLP. I actually have some ideas on it that we're exploring, but yeah, I think that's the only way.
I think I'll take the prerogative and ask the last question, which is what's a quasi-recurrent neural network?
Boom! Thank you. That last thing leads me to the last obstacle I didn't get to talk about. Basically, we talked about the LSTM, right? In the LSTM, we had at each time step kind of depended on the previous time step, right? We can't compute the next hidden state until we have the previous hidden state. And while I love recurrent neural networks for their generality, that's kind of not great for GPUs, right? Because GPUs, we want to do the same thing in parallel across a lot of different dimensions. And so what we basically, CNNs are really good at that. You can completely, like max-bill in parallel, you can do lots of convolutions of all the different filters on the GPU in parallel, and so on. And so all these steps are parallelized. And so we basically tried to combine the best of these two worlds, and that's what led us to quasi-recurrent neural network, where we compute gates here with similar kinds of ideas of gates, of outputs and updates and so on. But look, they're not depending on ht minus 1. They're just of two time steps that are next to each other. So when you do this kind of thing, that is essentially a convolution that you can rewrite this if you say, all right, my filter size is 2 word vectors at a time. So that you can completely parallelize over an entire input. And then the gates here are already parallelizable because they're element-wise. Right? They're element-wise gates. And so this you can also parallelize, but now across the feature dimensions. And that means you now have 2 parallelizable operations, and that leads you to immense speedups where you sort of always have some overhead, you always have some softmax, but now your recurrent part of this model is a lot faster. You can get, depending on your sequence length and your batch size, between 1.3 to like 16x speedups over general LSTMs. And we're now using these and trying them for lots of different ways. And in many cases, they're either the same or work slightly better in terms of accuracy, but they're always faster. And in some cases, also more interpretable. So that's the answer on QRNN.
The last word.
All right.
Thank you.
Thanks to the question askers. So great questions.
Archive on that, right? I'm sure.
Yeah. It's all, We also have a little bit of code snippet.
So we actually have to get out of the room for.
Yep.